तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in the last few classes we have looked at the CMOS logic circuit and some of its variations, our efforts to improve the performance of CMOS circuits. Today's class we shall again look at another variation of the CMOS circuit. Now, before going into that, let us first look at the advantage of CMOS, of a CMOS gate in comparison with other logic families in the MOS family. Well, the CMOS, as we know, the major advantage is that it has a zero static power dissipation. That is because in the under static conditions, when the NMOS is on, the PMOS is off, and when the PMOS is on, the NMOS is off. So, there is no actual current flowing between from the supply to the ground. Okay. So, the static power dissipation is 0. The only power dissipation only occurs when the output is switched from one level to the other, from output high to output low or from low to high. So, that is the hallmark of a good circuit, that is the power dissipation, the power is mostly consumed in switching, okay, and there is no wastage of power in the static condition. Well, CMOS also has another advantage, that is the output low is not determined by the sizes of the transistors. That is, it is basically a non-ratioed logic in the sense that the output low does not really depend upon the ratios of the widths of the individual transistors, which is true in the case of other logic NMOS logic families, MOS logic families, because for example, in the logic family with a depletion mode load, the load transistor is always on. So, the output low will be determined by the widths of the individual transistors. So, this is not the case in the case of CMOS. So, in fact, one can use a small dimension, one can use the minimum size transistors, because the output voltage is not really determined by the sizes of the individual transistors, which of course results in a saving in area. So, that is the basic advantage of that is one of the advantages of CMOS when compared to other logic families. Now, another advantage would be while switching, when the output is to be charged, say we have an output capacitance and the output voltage has to switch from low to high, that is the output capacitance has to be charged. Then what happens is the NMOS transistor is off and the PMOS is on, and the current flows through the PMOS to charge the output capacitance. So, in this case since the NMOS is on, the entire PMOS current can be used to drive the output capacitance. On the other hand, when the output has to go from a high to low, that is this output capacitance has to be discharged, then what happens is that the PMOS is off, the NMOS is on, and the entire NMOS current can be used to discharge the output capacitance. So, the PMOS does not, the PMOS is, since the PMOS is off, which is not the case of other logic families, like again the NMOS logic families, where the load transistor would always be on, with the result that the current which is discharging the capacitance is the difference of the currents of the driver transistor and the load transistor. So, this is a major advantage. Of course, here one must also point out that since the PMOS with the same dimension of the NMOS transistor, NMOS and the PMOS transistors are the same, then the PMOS would have a lower current because of the lower mobility of holes. So, in fact, if one has to go for equal on and off times, then one has to increase the width of the PMOS transistor. But that is a small disadvantage. The major advantages, so in the case of a NMOS, is that we have 0 static power dissipation, and also we can have minimum, almost minimum size transistors, and also while switching on and off, since the two currents do not clash, one can have fast switching also. But also even with these advantages, and also acknowledging the fact that the CMOS has been the mainstay of the VLSI for a long time, okay, this is not the ultimate circuit, in the sense that there is also a lot of improvements which can take place. For example, CMOS is not the fastest logic family. Okay. The fastest logic families are still the bipolar logic family, that is the ECL. Okay. And the main reason for this is that for the bipolar transistor, the transconductance is the highest. Okay. The bipolar transistor has a much higher transconductance than MOS transistors because of the exponential relation of the output current with the input voltage. So, that is a major advantage of the bipolar transistors, and also the current drive capability of bipolar transistors is more than that of the MOS counterparts. So, if one has to drive a large current, okay, one would prefer to use the bipolar transistor, because if one has to drive the same current with a MOS transistor, one would require a huge size transistor which would take up a lot of area. So, basically the bipolar transistors have certain inherent advantages, that is the higher transconductance as well as larger current drive capabilities, which also makes them very highly suitable for high speed logic circuits. So, on the one hand we have the advantage of CMOS, that is 0 power dissipation, static power, 0 static power dissipation, and some other advantages, while on the other hand we have the bipolar transistors have certain advantages, like being a high speed logic family, by being a high speed device, in the sense you have higher transconductance. Now, if we can have a logic family which derives the advantages of both, that is, we have on the one hand a logic family which has a 0 static power dissipation, okay, and on the other hand it has a very high current drive capability, that is, it can drive large currents to charge and discharge the output capacitances, okay. Then of course it would, using the bipolar transistor, then of course it would be sort of the best of both worlds, okay. So, that is what is attempted in the BiCMOS logic family, where you have, which is basically a CMOS circuit which includes bipolar transistors in the driving part, okay, where use a bipolar transistor to drive large currents at the output currents, okay, and this is used to speed up the circuit and give better performance. Okay. So, we shall discuss this BiCMOS logic circuit in today's class. Okay. Let us look at the BiCMOS inverter. Okay. What you have is a PMOS which is driving a bipolar transistor, and then you have an NMOS which also drives another bipolar transistor, and this is the input here, and we have the output here. So, this is supply voltage. So, you have V in and you have V out. Okay. So, the input side, it is like a CMOS, okay. You have a PMOS and a NMOS, okay, and which are shorted and connected to the input. Okay. Now, what happens is when the input is low, say 0 volts, okay, this NMOS will be off and the PMOS will be on. Okay. Now, when the PMOS is on, a current will flow in this direction, okay, and this current forms the base current of the bipolar transistor. So, if the PMOS current is ID, if we say it is ID, then the bipolar base current, the base current of the bipolar transistor is ID. So, a current, you would have an output current beta plus 1 times, because the output current is actually the emitter current of the bipolar transistor. So, beta plus 1 times ID, that is the current which flows and is going to charge the output capacitance. Okay. On the other hand, since the NMOS is off, okay, NMOS is off, then the base current of this lower bipolar transistor is 0. So, this lower bipolar transistor is off. So, it is not conducting. So, when the upper bipolar transistor is conducting, the lower bipolar transistor is not conducting. So, basically once this output capacitance is charged, okay, then once then the current dissipation then there will be no current flowing, because although the upper transistor would be in a conducting state, the lower transistor is off, and so there would be no static current flowing in this logic gate. On the other hand, if you look at the other situation, when the input is high, say VDD, then the you have a high gate voltage for the NMOS transistor here. So, this NMOS transistor is on, whereas this PMOS transistor is off. Okay. Now, since this NMOS transistor is on, a current would flow in this direction. Again, this current is going to be the base current of this bipolar transistor, and since we have a current ID, which is actually the drain current of the MOS device. So, if the base current of the bipolar transistor is ID, then the total current which is flowing, okay, which is actually going to be in this direction now. Okay, that is the total current is the sum of the collector current of this bipolar transistor plus the drain current of this MOS. Okay. So, that is going to be beta plus 1 times ID again, but it would flow in the opposite direction and it would help to discharge the output capacitance. So, when the NMOS transistor turns on, a current would tend to flow in this direction, in a direction which discharges the output capacitance. Okay. So, it is going, the discharging current is now beta plus 1 times ID. On the other hand, since this PMOS transistor is now off, okay, because you have a high input, okay, the PMOS transistor is off, then there is no base current for the upper bipolar transistor here. So, this upper bipolar transistor is going to be off. So, when the lower bipolar transistor is on, the upper bipolar transistor is off. So, again we have in the steady state we would have no static power dissipation. So, once the output capacitance is discharged, then no further current would be flowing. So, because although the lower transistor is in a conducting state, the upper transistor is in the non-conducting state. So, you see, if you look at this circuit, it retains the advantages of the CMOS, in the sense that again when the upper half is conducting, the lower half is off, and when the lower half is conducting, the upper half is on. So, both upper half and lower half are never on simultaneously in the steady state. So, the static power dissipation is 0. On the other hand, if you look at the advantages compared with CMOS, we find that the charging and discharging currents are now beta plus 1 times ID, whereas in the case of a CMOS, the current which was driving the output capacitances, the charging or discharging the output capacitance was only ID. So, we have a gain of beta plus 1. So, although this circuit retains the advantages of the CMOS, it has an additional gain of beta plus 1. So, since we are now charging and discharging the output capacitances with a higher current, okay, the time required to charge or discharge the capacitance would be less, in the sense that the operation would be speeded up. So, this is going to operate at a much higher speed than the corresponding CMOS. So, this, if you look at the delay curves of the CMOS and the BiCMOS, if we plot the delays, this is say the delay, and you have the capacitance, load capacitance. Okay. Now, for a CMOS, if it goes like this, okay, we know that the current, if you write, you can write I is equal to C dV dt. So, if delta V is the logic swing and the time is delta t for the output capacitance to change by delta V, and if this of course assumes a constant current is used to charge or discharge the capacitance. So, we can write T d is equal to C delta V by I. Okay. So, the slope of this curve is going to be delta V, which is the logic swing by I. All right. Now, if we, this is for the CMOS, whereas for a BiCMOS, what we have now is this current, which is the current for the ID, if we call the drain current in the case of CMOS. This is the drain currents which are used to drive the capacitances. Now, for a BiCMOS, since the current which is now charging or discharging the capacitance is beta plus 1 times ID, we have a curve like this. The slope is going to be, this is the slope. The slope of the curve is going to be reduced. So, you have delta V beta plus 1 ID. This is the slope for the BiCMOS curve. So, we will see that for the BiCMOS, okay, even with a large change in capacitance, the delay does not change by much, whereas in the case of CMOS, if you are driving a large capacitance, the delay changes much. Of course, initially for very low capacitance, the BiCMOS may have a slightly higher delay because of the fact that you are introducing additional components in a BiCMOS, but especially for larger capacitances, okay, because of the fact that the delay is almost flat, okay, for larger capacitances, the BiCMOS will have will be at a much greater, will be operating at a with a much lesser delay compared to the corresponding CMOS circuit. So, that is the advantage of BiCMOS compared to the CMOS. Okay. There is a small disadvantage, okay, which we shall also point out here, and we shall discuss in detail sometime later. Okay. The disadvantage in this case for the BiCMOS is that when the output voltage, for example, when we are charging the output capacitance and the PMOS is on, okay, when the PMOS is on, then this bipolar transistor gets a base drive, the output capacitance is getting charged, the output voltage rises. But once the output voltage rises to VDD minus VBE, when the output voltage is equal to VDD minus VBE, okay, that is VBE is the base emitter drop of the bipolar transistor, okay, then what happens is say VBE is 0.7 volts, okay, or V on of the bipolar transistor, then what happens is after that if the output were to rise further, then the base emitter drop of the bipolar transistor would reduce to below V on, which means that it is no longer going to be in a conducting state. Okay. So, the output voltage will rise to almost close to VDD, that is VDD minus V on, very fast because of the action of the bipolar transistor. After that, what happens is, because we require a certain voltage drop across the base emitter of the bipolar transistor to maintain it in the on condition, the output voltage would stop rising any further. I mean, it will rise, but very, very slowly. Okay. Also, similarly, when the output capacitance is going to be discharged, the current which flows through into the bipolar transistor as well as the drain current of the MOS. Now, here again, the base voltage of the bipolar transistor has to be around 0.6 to 0.7 volts. Okay. Now, when the output voltage falls to that value close to 0.6 volts, okay, what happens is this voltage, collector voltage, becomes equal to the 0.6 volts. It cannot fall any further because then the base emitter voltage is going to be below 0.6 volts, which means that this bipolar transistor is going to draw a very small current, okay, and the discharging becomes extremely slow. Okay. Also, since the drain current of the NMOS should flow into the base of the bipolar transistor, the NMOS would also stop conducting. So, the logic swing of the BiCMOS, okay, it is not a full swing, that is from 0 to VDD as in the case of CMOS, but in the BiCMOS the output voltage would go from V on to VDD minus V on. So, the swing is from V on to VDD minus V on, where V on is the cut in voltage of the base emitter of the bipolar transistor, which would be around say 0.6 to 0.7 volts. Okay. So, it will go from this. So, if you have a 5 volt operation, it would go from say 0.6 to 0.7 volts to around 4.4 volts or so. So, you do not have full swing operation here. Okay. So, that is one disadvantage of the BiCMOS when compared to the CMOS. Okay. We shall look at the implications of this sometime later. Now, but in general we see that the BiCMOS has a lot of advantages compared to CMOS, in the sense it retains the advantage of CMOS as being zero static dissipation circuit. At the same time, because of the gain of the bipolar transistor, it is a much faster circuit compared to a CMOS, especially when driving large load capacitances. Okay. Then okay, there is one more point to be looked at in this bipolar in this BiCMOS. Well, one point is of course that this bipolar transistor really one good one advantage is that this bipolar transistor does not really go to saturation. Okay. I mean why? Because since the emitter voltage of this bipolar transistor can only rise to VDD minus VB, and this is always at VDD, which means that the collector to emitter drop of this VCE of this bipolar transistor is always going to be at least 0.6 to 0.7 volts. So, it does not allow it to go to saturation. Also in the lower transistor also, since the output voltage does not fall to below 0.6 volts or so, this collector emitter drop is at least 0.6 volts. So, it does not go to saturation. But even then, what we would like to do is, once the input voltage changes state, for example from low to high say, okay, then what is going to happen is, when the input voltage was low, the PMOS was conducting and the NMOS was off. So, this transistor was on, upper transistor was on, this was off. So, as this goes from low to high, this should go from on to off, and this should go from off to on. Now, this on to off should take place at a very quickly. Okay. Otherwise, what is going to happen is, we are having a high speed circuit mind you. So, this we require this off to on to go should also take place very fast, that is, output capacitance should be charged very fast. Sorry, the output capacitance should be discharged very fast, because the lower transistor is going from off to on. So, the discharging current is through this lower bipolar transistor. Okay. Now, if this upper bipolar transistor does not go off fast, then this current is going to actually affect the switching off or the discharging of the output capacitance, because the current which is going to discharge the output capacitance is going to be the difference of this current drawn by the lower transistor and the current which is the emitter current of the upper transistor. So, that is going to be the difference. So, this upper transistor must switch off fast. So, we should ensure that this switching off is done fast. So, how do we ensure that? You see that there is no real mechanism in this circuit for a reverse base current to flow for the bipolar transistor. We have always stressed that when we discussed bipolar logic families, that in order to switch off the transistor fast, we must have a reverse base current flowing, which draws out the base charge and switches off the bipolar transistor fast. So, that is one drawback in this circuit in this present form, because there is no mechanism to remove the base charge. Now, let us see how we can improve this circuit by introducing small changes, so that it can switch off faster. So, what is done is, we have a circuit like this. This is the NMOS here. We have the bipolar transistor. So, this is the input here. Okay. There is another NMOS here, and this NMOS input is drawn from here. So, this is the new inverter. Okay. Now, what we have added, if we just compare these two circuits, okay, which are so what we have added in the new circuit here is that we have added an NMOS here, okay, and another NMOS here. Now, these two NMOSs, as we shall see, as we can see, are connected to the base of the bipolar transistor and are basically used to draw out the charges from the base of the bipolar transistor when these transistors have to go from on to off condition. So, when you have a similar transition at the input, that is low to high, this input, then this lower transistor should turn on from off condition and the upper transistor should go from on to off. The upper transistor should go from on to off. So, what happens is, as this goes high, then this NMOS transistor is going to turn on from the off condition, and this is going to conduct and discharge whatever base charge was is there in the bipolar transistor and help it to switch off faster, because this NMOS is turning on. So, again and this transistor is going to go from off to on. So, basically when this was low, okay, so this is an inverter here. You see that we have a Cmos inverter here, and the output of the Cmos inverter is actually fed as input here to this NMOS, and which is connected to the base of the bipolar transistor. So, this is going to draw out the base charge from the bipolar transistor. Okay. So, what happens is, when the input is low, here the input, this is a Cmos inverter, this is high, and this the input to this NMOS transistor is high. So, this is on, okay, and it maintains this transistor in the off condition. Okay. So, when this output again goes from high to low, okay, from high to low, then what happens is, this output of the CMOS goes from low to high, okay, and this turns on this transistor, which helps it to discharge the base whatever base charge in the bipolar transistor. So, we have two additional transistors here, okay, which help in to discharge the output to discharge the base charge of these bipolar transistors. So, this is the basic form of the BiCMOS inverter. Okay. We can also have other logic gates as in the CMOS, for example, a Nand gate. Now, what we have to do is, in the case of a Nand gate, we know in the case of a CMOS, we have two PMOS transistors in parallel and two NMOS transistors in series. So, if we want to have a Nand gate in CMOS, this is the circuit. Okay. Now, in the case of a BiCMOS, what we would do is, this goes to the base of the bipolar transistor, and we have the lower bipolar transistor here. Okay. So, this goes here, this other input, actually we draw it here, then the output of this CMOS here in the CMOS NAND gate goes to the gate of this NMOS here. Okay. So, this completes the circuit for the CMOS, the BiCMOS NAND gate. Just I'll explain it once more. So, this is there are two inputs here, BiCMOS NAND gate A and B. So, what happens is, when the input in a NAND gate, we know the output goes high when any input is low. Okay. When any input is low, the output goes high, and when both inputs are high, the output is going to be low. Okay. Now, when both inputs are high, Okay. Both these lower NMOS transistors are going to conduct. So, both these are conducting as well as these two are conducting. Now, since these transistors are in series, say the lower half, this is in series. Okay. When these are conducting, there is a current flowing this way into the base of the lower bipolar transistor, and so the lower bipolar transistor is going to be on. Okay. And it is basically going to discharge the output capacitance. So, the output voltage goes low. So, when this goes high, this goes, when both these go high, okay, the output is going to go low. And also when both these are high, then these PMOS transistors are off. Okay. So, this upper bipolar transistor is off, whereas these two transistors are also on. Okay. These two NMOS are on, which enables the discharge of whatever base charge is in the upper transistor. Now, if any input goes low, when any input goes low, so high to low, say here, what is going to happen? When this any input goes low, then one of these NMOS transistor, this NMOS transistor is going to switch off, is going to go in the off condition, which means that in the series path is not conducting, which means that the lower bipolar transistor is not going to have any base current, which means that the lower bipolar transistor is not going to conduct. So, the lower bipolar transistor is off. Now, at the same time, this bipolar this is basically a Cmos NAND gate. Okay, this Cmos NAND gate, when any input goes low, the output is going to go high. You have a high here. Okay. And which means that it turns on the upper bipolar transistor, which and this, there is a current flowing in this direction, okay, which is going to charge the output capacitance, and the output is going to have a low to high transition. Okay. Output is going to have a low to high transition. At the same time, since this goes high here, this gate voltage of this NMOS transistor here is going to go high. This turns it on, and since this is connected, the drain of this NMOS is connected to the base of the bipolar transistor, a current is going to flow out from the base of this bipolar transistor and help to remove any base charge stored in the lower bipolar transistor, thus speeding up the switching off of this bipolar transistor. So, the upper bipolar transistor turns on, the lower bipolar transistor turns off, and a current flows out to charge the output capacitance, and you have a low to high transition. Okay. So, this gives the circuit of a CMOS NAND gate. Okay. So, where you basically have what we basically have is, we have a CMOS NAND gate here. This is a BiCMOS NAND gate. So, we have a CMOS NAND gate here. We have the N block of the CMOS here. Okay. N block of the CMOS here, which is actually driving the lower bipolar transistor, and then the output of the CMOS NAND gate is driving the gate of this NMOS transistor here, okay, which is helping to switch off the bipolar transistor. So, now if you look at any BiCMOS circuit, okay, we can actually derive it from the CMOS logic circuit by drawing it in this form. We shall draw a general BiCMOS logic circuit. Okay. So, what we have is, we have a CMOS gate here. So, if it is if we are making a BiCMOS NAND gate, we will have to make a CMOS NAND gate. If we have a BiCMOS NOR gate, we will have to make a CMOS NOR gate. If we want any other logic function, so this is the CMOS equivalent of the whatever BiCMOS logic circuit we want to make. So, these are the inputs here, okay, for that CMOS. Then the output of that goes to the base of the bipolar transistor, okay, and this is connected to the VDD supply voltage. Okay. Now, what we have is, we have another bipolar transistor here, and then what we have is, here we have the N block of the CMOS, that is the lower half of this CMOS. Okay. The N block is connected to this another bipolar transistor, and this goes to ground, and this goes to ground here, and then the output of the CMOS drives another NMOS transistor here. Okay. So, this goes to the gate of this NMOS, which is connected to the base of the bipolar transistor. So, the inputs again come here. Okay. Now, what happens is, suppose we have some inputs and for that set of inputs we must get a logic high. Okay. So, say now what happens is this CMOS, which is actually also realizing that particular function. So, what will happen is this output here is going to go to logic high. Now, when does in a CMOS the output is going to go high when the P block conducts and the N block is off, which means that if this output is going to go high here, okay, this N block is going to be off. Okay, because this is the same CMOS, this is the N block of the CMOS, which is the lower half of this CMOS circuit. So, this is going to be off. Now, if the N block is off, the lower transistor is off, you have a high at the base of the upper bipolar transistor, which means that it conducts, and also the gate of this NMOS transistor here as a high, which means that this also conducts, which removes the charge of the base charge of this lower bipolar transistor. So, the upper bipolar transistor conducts, the lower bipolar transistor is off, so the output is going to go high. Okay, and the output current is increased by the current gain of the bipolar transistor. Similarly, if for a particular set of inputs the output should go low, then we will have a low here. Okay, and the N block should conduct, because the output is low in a CMOS when the N block conducts, which means that the lower bipolar transistor will have a base current, okay, which means that this current is going to discharge the output capacitance, and also since this is low here, this NMOS is off, which means that it is not really affecting the output, it is not going to have any effect on the circuit. Also, since this is a CMOS, you have an N block here which turns on, okay, and that N block here in the CMOS is going to discharge whatever base charge is there in this upper bipolar transistor. So, in this case the output is going to go low, because the lower bipolar transistor turns on, the upper bipolar transistor is off. So, this is the basic circuit of the CMOS, of the BiCMOS, any BiCMOS gate. So, any CMOS gate can be converted to a BiCMOS using this particular circuit. Okay. Now, okay. Now, this BiCMOS obviously has a lot of advantages compared to CMOS, as we have already seen, but we also said there was one particular disadvantage, that is we are not having full logic swing. This particular disadvantage is it really shows up when we go for low voltage circuits. See, up to a long time the power supply voltages in logic circuits were 5 volts, that was a standard which was used, but in recent days the power supply voltages are being continuously scaled down. There are mainly there are lot of reasons for that. One is that as we are going for smaller and smaller devices to improve the speed as well as to reduce the power dissipation, the smaller devices cannot take so high voltages, because the electric fields becomes too large, okay, with the result that there can be breakdown problems. So, as we reduce the dimension of the device, we must also reduce the power supply voltages. The power supply voltages are also reduced to reduce the power dissipation. Okay. So, in order to do that, if we reduce the power supply voltages, it really creates problems in the case of BiCMOS. Now, if you look at this circuit here, okay, when you have an input voltage, whatever input voltage is applied here, okay, if this voltage is now VDD minus VBE, okay, if you have another VBE here, okay, so the actual voltage for the NMOS is VDD minus twice VB. That is also clear here if we go back to this circuit. Okay. So, this if it is VDD minus VBE, okay, and you have a VBE here. So, what we have is VDD minus twice VBE, okay, across the gate to source of the NMOS. So, you know that the current in a NMOS is proportional to VGS minus VT. So, if the VGS is in this case is now VDD minus twice VBE, in the case of BiCMOS minus VT, okay, squared. Okay. Now, but of course, you have a current gain of beta, okay, almost beta, if beta is high, beta plus 1 can be approximated as beta. So, for a I of a BiCMOS by a CMOS, okay, that is this charging and discharging currents, we will have VDD minus VT whole square. In a CMOS, the entire voltage is dropped across the transistor, there is no 2 VBE drop. Now, if you look at a 5 volt power supply and say suppose beta is 50, when beta is 50, VDD is 5 volts, say VBE is 0.8 volts, this is usually the at a higher side, but for smaller devices you usually have that, and say VT is equal to 1 volt. Okay. So, this ratio R, let us say, will be equal to 50 into 5 minus 1.6 minus 1 squared divided by 5 minus 1 squared. So, this is 50 times this is 2.6 into 2.4 squared divided by 4 squared. Okay. So, this is basically 0.6 squared, that is 0.36. So, this will be around 18. So, the current gain which we have due to BiCMOS, although we are having a beta of 50, is only 18 here, because this is reduced because of the VBE drop in the reduction in the logic swing of the due to the bipolar transistor. Now, this problem is going to be more severe as we go for low voltage circuit. Suppose the VDD is now 3 volts and VT of course will be also reduced if you have a 3 volt circuit, say is 0.6 volts, then this ratio is going to be equal to say 50 3 minus 1.6 minus 0.6 squared divided by 3 minus 0.6 squared. Okay. So, this is going to be 50 into this is 2.2, so 0.8 squared divided by 2.4 squared. So, this is 3. So, 50 by 9. So, it is almost about 5 or so. Okay. So, this ratio is further reduced. So, we see that as we go for low and lower voltage circuits, okay, this ratio is reduced. So, the advantage of BiCMOS is severely reduced, okay, as we go for lower and lower voltage circuits. So, if we go for say 2.5 volt circuits for example, then the BiCMOS would not be as advantageous as a CMOS. So, there have been lot of circuits which has come up, okay, which try to operate which would like to retain the advantages of BiCMOS even at low voltages. So, what is done is we have low voltage BiCMOS circuits, okay, where an attempt is made for full swing operation. I will just give one example, okay, which has been used in the Pentium chip. Okay. So, what they do is we take a Nand gate. So, you have a this is basically a CMOS NAND, okay, then which goes to the bipolar transistor here, and then you have here the pull down is actually done with the help of NMOS. Okay. So, we do not use the PMOS, we do not use a bipolar transistor in the pull down because of the fact that at low voltages it is no longer advantageous to do a pull down because of the extra VBE drop. One must also remember that here, okay, if you go back to this circuit. So, here the difference here is that this voltage here for the NMOS, the source voltage becomes VBE. So, if you have VDD minus VB here, so it becomes VDD minus 2 VB across this. But here, since the source of the PMOS is always at VDD, the gate to source voltage of the PMOS is not so much affected as in the case of NMOS. So, what is done here is we put an inverter here, okay, and then follow it up with a PMOS. Okay. So, this is basically the circuit. There are some other additional circuitry here, okay, which is for to prevent the breakdown of this transistor, but we will not go into that. But the basic idea here is that these are the two inputs here. Okay. Now, when the output goes high, okay, the output capacitance is going to charge up when but only up to VDD minus VBE by this bipolar transistor. After that, what happens is, since this output is high, we have an inverter here, this is also a CMOS inverter. So, this the PMOS input voltage is low, which turns on this PMOS. So, what happens is, this output voltage goes to VDD minus VBE, the bipolar transistor helps to pull up the output to VDD minus VBE. After that, the PMOS is there to pull it up beyond that towards VDD. So, the output is going to go to VDD, okay, because of this PMOS. At the same time, it will also go to 0 because you do not have any bipolar transistor here. So, we have full swing operation from 0 to VDD, okay, and so a lot of these circuits are being developed nowadays for full swing operation, keeping in mind the low voltage operation. Okay. So, this is a particular circuit has been used in Pentium. In fact, there are different variations of these full swing BiCMOS circuits by different groups of people from different companies. Okay. And but the basic idea is, what we see basically is, for the pull down part, the NMOS, it goes back to the NMOS, okay, there is no bipolar transistor, but for pull up the bipolar transistor is used, okay, which helps to speed up the low to high transition of the output. Okay. So, with that we come to the end of this section on BiCMOS, basic BiCMOS circuitry. We shall take up some more applications of this BiCMOS in the next few classes.